赛前主办单位要我们提醒各位队伍那第一件事情就是比赛期间不可以使用网络，不可以录音，不可以录影。OK， 然后第二件事请不要在投影机前面放置遮光物品它会损害投影机。OK 好，那好，那我们就等时间到就开始。好，那我们时间到就正式开始这一场比赛。好，那首先我会先介绍我们这一场的评审那第一位是中原大学的翁文玉教授。那个在中心的许宏伟教授，然后是东吴大学的林志渊教授，中正大学的陈功教授，我是高雄中学的卢在良老师。好，那请各队介绍队伍的成员请reporter先
I'm the captain from We Go 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 Go. My name is Naomi, and here's Stevie, Henry, Linus, and Eugene. Thank you.
好，再是 opponent.
I'm the captain of Team Celsius, and I'm Lin Chuanqi. She is Liu Helong, and he is Su Datong. He is Zheng Zhongyang, and he is Deng Guishen. Thank you.
Okay. 好，那 reviewer.
I'm the captain from Variable One, and I'm Yang Youyi. She is Chen Yaoqi. She is Chen Xuanzi. She is Guo Weixin. She is Yan Yunhong. Thank you.
Okay. 好，那我们就正式开始这场比赛。好，那请计时器开始计时。好，那第一个是 opponent change the reporter for the problem. 1 minute.
You want to try problem 1, paper boomerang.
Okay.
We reject.
Reject. 好，那请 opponent 再选择第二个。
We're going to try problem 5, dancing city.
We reject.
Reject. 好，那再请第三个。
We want to challenge problem number 14, water bottle rocket.
We accept.
好，那请各队到黑板写上担任 reporter、opponent 跟 reviewer 的姓名。 Okay, hands up. Presentation of reporter. 12 minutes.
Honorable judges and worthy opponent, this is the reporter from Team We Go 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 speaking. And in this presentation, we're going to discuss problem 14, water bottle rocket. Starting with the problem statement. When we pump air into a plastic water partially filled with water, and under certain conditions, the bottle is launched and flies into the air, and we're going to investigate how the acceleration during liftoff depends on relevant parameters. In this presentation, we're going to be focusing on two main things. Firstly, we're going to discuss the relevant parameters and also the theoretical acceleration. Here is a simple video of the phenomenon. As you can see, when we release the water bottle rocket after air is pumped into a water bottle, the water bottle rocket will fly off vertically to the ground. And here is a simple diagram. Throughout the experiment, we have several observations and assumptions. Firstly, we found out that the rocket will tumble before reaching maximum height. And also, we shoot the rocket 90 degrees up, which is vertical to the ground. And we assume that we only consider only lift-off of the rocket launch. To define lift-off, we define it as 0.1 second after we release the water bottle rocket. So as a result, we can also assume that it is a pseudo 1D motion. Okay, starts the equation deviation. Starting with the conservation of momentum in the system. We assume that the water bottle rocket is launched in some kind of place with no extra forces acting on it. So we have the initial momentum as mv and the final momentum as shown here. To get our first equation, the force of the thrust equals u times dm over dt. And then we consider it as an adiabatic expansion, since the volume of the gas expands very quickly when water exists. So we have equation 2. And we also apply Bernoulli equation to get equation 3. By applying the Bernoulli equation, we have several assumptions. First, we assume that the flow velocity at the air-water interface inside the rocket body is negligible compared to water output rate. And due to rocket's elevation difference as it flows from inside to outside the rocket, the change in gravitational potential energy of water is negligible. We also assume that the water flows under quasi-static conditions, so that the effects of fluid friction are negligible. And so, since we know the mass flow rate is equal to the water output rate, we have equation 4. Combined with thrust, substitute thrust into Bernoulli equation to obtain equation 6. By combining equation 2 and 7, we can get equation 7. 2 and 3, we can get equation 7. Then differentiate for u in function of time to obtain equation 8. Then we know that the rate of change of the air volume inside the rocket is equal to the rate of water existing in the rocket. And by combining equation 8 and 9, we can have the equation 10. And substituting v, which is volume, we can get equation 11. Integrate equation to solve u, which is the rate of the water output, which equals here. And at t equals 0, which basically is when we release the water bottle rocket, we can solve u0 by equation 3 and further calculate the thrust with equation 5. Well, then we want to calculate the extra force acting on the rocket. So firstly is a drag. We need to calculate the real numbers of the air, which comes out to be more than 1,000. So we can assume that the drag is a quadratic drag. So we can have equation 14 as a drag equation. And apply thrust to an equation 12. To measure the drag force, we do a preliminary experiment to test out what is the drag coefficient. It comes out that without fins, the drag coefficient will be 0.345, and with fins, the drag coefficient will be 0.542. Here is a basic experimental setup of our water rocket launching. First, we use an electrical pumper that we can control the pressure pumped into a water bottle rocket. And here we have launcher, so we can control the point and the time we release the water bottle rocket itself. And then we capture the motion of water bottle rocket with this super slow motion camera. To ensure the most stable launch, we bring the commercially sold nozzle to neglect friction and optimize the motion. We also smooth the inner surface with drill, also to, again, minimizing the friction effect. Well, here's boundary condition for this water bottle rocket launching. In order for the rocket to launch, the minimum amount of water and air required is 55 milliliter and 30 psi to launch inside our 485 milliliter plastic water bottle. And we also found that the visible deformation of water bottle rocket occurs when the pressure reaches 110 psi. As a result, we state the range of the pressure from only 30 psi to 70 psi to minimizing the deformation of water bottle rocket. Okay, starting our experiment. First, we want to investigate the effect of increasing the water amount while keeping the pressure stable. Here's parameters of this experiment. For water volume, we start from 100 milliliters and increase by 50 milliliters. And pressure, we do two groups of experiment, one with 30 psi, another with 70 psi. We shoot the rocket without the fins, and also the rocket mass is not added any other weights, so it's 0.053 kilograms. So here's our theoretical graph, and here's our experimental graph. You can see that as water rises, acceleration decreases at each time interval. And as we add more water, the acceleration will also decrease. Here is the experimental group with 70 psi. Also, we can assume the same thing. Then we want to investigate the effect of increasing the pressure while keeping the volume of water stable. In this experiment, we fix the water volume at two separate experiment groups, as one is 100 milliliters and another is 300 milliliters. And for pressure, we start from 30 psi and increase by 10, again with no fins and no extra weights. The thing we observe is that as we pump more pressure, the acceleration will increases. And the same result comes with the 300 milliliters group. Then we want to investigate the effect of using fins while stabilizing other parameters. So here we do 4 separate experiment groups, one with 100 milliliters, 300 milliliters, and 30 and 70 psi. And the parameters we change is we use fins or without fins in the water bottle rocket. And again, the weight is not changed. Well, here's a small explanation on how we thought the fins will influence the water bottle rocket. Well, the fins counteract sideways motion of the water rocket. Air flows smoothly past them if the rocket is traveling along its axis. And if there is any sideways motion, then the air striking on the fins pushes the rocket back towards straight motion. While fins improve stability, they also increase the rocket's drag coefficient. It's also shown in our preliminary experiment. And we thought this is because the additional surface area of the fins creates more resistance as air flows around them. And here is the experimental graph of it. So we can see that there's very small influence of fins to the water bottle launching, since most of the influence, such as drag and the stabilizing, will affect mostly while it is flying on the air. Finally, we want to investigate the effect of increasing the weight while keeping the other parameters stable. Again, we fix the water volume at 100 milliliters and 300 milliliters. While we stable the pressure at 30 psi and 70 psi, and we shoot the water bucket without fins. However, in this case, we do two separate groups for weight, one with no extra weight and one increase the weight by 15 grams. It comes out that the more weight will affect the lower initial acceleration. However, extra weight reduces the initial acceleration of a water bottle rocket. Because air-resistant affect heavier rocket mass, the acceleration of a lighter rocket will decrease more quickly. So as you can see, this is a lighter water bottle rocket. In conclusion, we have four conclusions. The water volume increase, the acceleration will decrease. As we pump more pressure, the acceleration will increase. When we add fins to a rocket body, so it will not affect the acceleration during the lift-off, but will stabilize the rocket for the entire duration of the flight. While adding extra weight reduces the initial acceleration of a water bottle rocket, the heavier rocket's increased mass makes it less affected by drag, causing the lighter rocket's acceleration to diminish more rapidly until their net acceleration may converge. And here's the future research we want to conduct later, which includes we want to investigate how different materials of water bottle rockets will affect the outcome, and how different shape of rocket tips and fins will affect the acceleration. And also we want to investigate how the water-air ratio will influence the outcome. Here is the reference of the presentation. Thank you for listening.
Question or opponent to reporter, 2 minutes.
Did you consider the effect of turbulence?
Well, as we mentioned, since we only
Yes or no?
no.
Okay. Does your model assume that the water flows out in a stable and uniform manner?
Yeah.
Did you assume that will the mass flow rate remain the same in the case of high water volume?
Yes.
Did you calculate that your mass flow rate calculation matches the observed water ejection rate?
Can you repeat that?
It means, did you actually measure the mass flow rate in your experiment?
No.
Did your model consider the effect of air resistance on the rocket's motion?
Yes.
Did you use pressure sensors to monitor changes in internal pressure over time? Did you measure the pressure throughout the process of liftoff?
No. That's atmospheric pressure.
So it's just the initial pressure.
Yeah.
Did you consider the effects of rocket lateral movement on acceleration measurements? It means does the rocket
No.
no? Okay. Did you check whether the rocket center of mass shifts significantly during the launch?
We know it will go down.
The rocket center of mass, does it change?
Yeah, it does change.
Does the water exit the nozzle completely parallel?
Yeah, it is.
Will there be a boundary that the rocket will not lift off?
Yeah, you mentioned in the presentation.
Okay. Thank you.
You're welcome.
Okay. Preparation of opponent for 3 minutes.
全部都是。他们拒绝题跟选择都写完了。有。都上面啊？都上面啊？都写完了吗？都在那边。
Opponent has the floor. Maximum 4 minutes.
Honorable judges and fellow competitors, I'm the opponent from Team Excelsior. Today I'm going to oppose problem number 14, water bottle rocket. Here's the problem statement. Today I'll mainly focus on what factors provide the thrust of the water rocket to launch and how will the parameters affect the acceleration. This is the reporter's outline. For the theory part, he mentioned the conservation of momentum and the Bernoulli's principle. He also calculated the transformation of the momentum. For the experiment and analysis, his parameters are the air pressure, the water volume, and the rocket weight and fins. And he always measured the acceleration throughout the experiment. And the reporter compared the theory with the data before the rocket. Here's some controversies and deviations about the reporter. Like they didn't give a clearly defined of the lift-off process, and they didn't consider the pressure change while lift-off. And here's are some strong and weak points that the opponent think the reporter did well and did not do well. The strong point of the reporter is they provided a clear observation video and they have a clear qualitative explanation. And they also explain the phenomenon well. But in the weak points, the deviation between the theory, they didn't compare the deviation between the theory and the experimental data. And they didn't consider the existence of air resistance, and they failed to optimize the precision and accuracy, and the tools used to measure acceleration are not accurate enough. And then is the points to be discussed. The opponent would like to discuss with the reporter for these points. For the parameters, we would like to discuss the air resistance and the water volume, which includes the weight of the rocket, the area containing the air, and the water volume which provided the force. And for the theory part, we would like to talk more about the mass flow rate and air resistance, and if the Bernoulli's principle is accurate enough to explain the phenomena. And for the data analysis, we will talk about some of the boundary conditions and the optimal water volume. And for the experiments, we would like to talk about the experimental setup, such as the measuring of the acceleration and the data collecting. And also, we would like to talk about some more extra parameters, such as the radius of the nozzle and some of the deviations that the reporter didn't mention in the report. The opponent would like to skip the
discussion.
So, since you didn't measure the mass flow rate throughout the lift-off process, did you assume that the flow rate will remain the same throughout the whole time?
Well, yeah, we do assume that the flow
So
rate
can you explain
will,
why can you?
Well, as we thought that we only investigate the first 0.1 seconds after releasing. So we also talked about how the gravitational energy won't change a lot.
Since according to your data, the acceleration of the rocket is about 100 meter per meter divided by the second squared, and with your assuming that the liftoff process is 0.1 seconds, it actually moves a long distance. How can you define that as a liftoff? It's about like 10 meters.
Okay. So, well, we do consider about the definition of liftoff, and after discussion, we found out that after 0.1, 0.2, there will be a lot of extra effect from drag and also the air motion striking from a sideway. So as a result, we decided to only consider the first 0.1 second after releasing the water bottle rocket.
We'll investigate from another aspect. Okay. Then, do you think that the air pressure will be affected by the space remains in the bottle? Like when do you think like the air pressures changing will be affected by the?
Yeah, we do.
Yes. So when the judges, can I use the blackboard? So, for example, if one water bottle rocket is filled with maybe 200 liters of water, and another is filled with 500 milliliters of water, the space for the air to remain will be different, right? Yes. Then, if you eject the same amount of water, do you think that the changing of the pressure will be different in these two conditions? Like, let me explain. So, so the rocket with the less space of air, when 10 millimeters is exploded, it also increases the available space by 10, right?
Yeah.
But the ratio between this part of the
Well, we do talk about we will do the water air ratio.
But in this condition, the changing of the space will affect more in it will affect the phenomenon, the air pressure more. So actually, since you didn't measure the pressure throughout the process, actually in this condition the air pressure would drop. Do you consider this situation? Can you explain how?
How? Because we state that P3 is constant, so when it's more volume, will obviously the pressure will drop.
I'm talking about the ratio between the.
Water and the.
No, I'm not. I'm talking about the
air
air and air, like the air here and the air here. The changing of the pressure, actually, would it be different? Like the.
Well, we think the changing of pressure, since we control the pressure which is added into the water bottle rocket, so as a result, there might be a small difference between the pressure difference because of the different volume and different air
Okay,
space.
thank you.
So
So I understand. So as you mentioned that the mass flow rate won't change in all experiments, can you briefly explain the reason you think the mass flow rate won't change?
well, we use mass flow rate as only one of the tools to get our final acceleration. So if you look at our PowerPoint, you can see that the mass flow rate aren't actually in the final equation. So,
You didn't consider the changing of mass over.
yeah, we think it's negligible, and it's also just only one of the tools.
Okay, next question. Do you think that, as you mentioned that you don't think air resistance will affect the phenomenon, right?
No, we do. We do. We consider it in the
But
draft.
I asked you in
No,
the.
you actually
and-
asked
and-
yes.
Okay, fine. Thank you.
There might be
So- Okay. Next is about the boundary. Do you think there will be a boundary for the most of the water volume?
Well, since the problem state that is partially filled with water, we assume that the water volume won't be the most. But like we see, like there's still place for air for pressure to give a force to the water, and also, yeah, there might be a boundary condition because of the extra weight the water gives to the water bottle rocket.
Okay, next question. Why is there a sideway motion, as you mentioned in the report, that if your experiment is fixed over 90 degrees upwards?
Well, the sideway motion, we talk about how the fins will mostly influence
Yeah, but
the.
why would this happen if your
Well,
experiment
there's air
is?
motion. There's air motion
No,
outside
now I'm
the
not
rocket.
talking about the fins. I'm talking about.
Yeah, there's air motion causing the water bottle rocket to tilt.
So it's about the wind, or
Also,
if the air in the environment is uniform, then it will not cause any side motion.
and
So
also we talk about how we want to consider changing the shape of the tip, which might be also one of the parameters, because maybe our experimental setup, our rocket tips isn't very precisely like centered in the tip point. The tip maybe is not in the very center, so it might cause an extra tilting force after 0.1 seconds. But however, when we are only consider the lift-off period, which we define as 0.1 second after releasing the water bottle rocket.
okay, thank you. Did you define the acceleration as only the y, y?
Yeah.
Oh, then okay. Then since there would be a side motion, did you consider
And we talk about how side motion will mostly affect it after 0.1 seconds, after the lift-off period. So during the lift-off period, what we observe and what comes out in our experiment diagram and also our theoretical diagram shows that this is a 1D motion.
Okay. And what do you think will happen if the radius of the nozzle changes? What do you think the difference between when the nozzle is this large and when the nozzle is this thin? The radius
Well,
of it.
We can obviously assume that if the nozzle is bigger, there will be a mass thrust. There will be
Yes.
mass thrust. Yeah.
And will it affect the phenomenon of the velocity of or the acceleration of the rocket?
Well, yeah, it will affect it. We also
Can
determine in the
you
presentation.
predict which one will be faster? The
The smaller one, because there's more thrust force.
first force,
Yeah, there's more.
according to the Bernoulli series.
Yeah, according to the Bernoulli theory.
Okay, thank you. Then, do you think there will be a boundary of air pressure that in your experiments that the water bottle rocket won't lift off?
You mean the minimum or maximum?
Minimum.
Yeah, there will be a minimum.
Why do you think there's a minimum?
Because when the pressure isn't strong enough to push the water down to create enough thrust to lift the water bottle.
But actually, with your the launcher and the bottle, there will be a friction between it. Do you think that friction will affect the lift off?
What friction? You mean
Between
the
the-
friction nozzle?
Yeah, the nozzle of the nozzle.
Nozzle and the launcher.
Yes.
Nozzle and launcher. So we talk about how we use the commercially sold nozzle, that's minimizing the friction back in it. Yeah, of course, it will affect the results.
So
but
you didn't calculate it in
Okay,
the
time's up.
of the.
Opponent, summarize the discussion for 1 minute.
Okay, this is the discussion summary of the reporter. So the reporter did not internally observe the flow rate of the rocket, and they cannot consider the initial 0.1 seconds of lift off for this experiment only. And they did not consider the changing air pressure within the rocket. And also, they did not consider the measure of the change mass flow rate in the experiment, while we the opponent suggests the reporter to actually measure it. And also, the reporter did not consider the shift of the center of the mass within the rocket with conducting the experiments. And the experimental conditions like the wind, the reporter didn't explain why there will be a side motion of the rocket, and the radius of the nozzle would affect the experimental
Question
results.
of reviewer
Thank you.
to reporter and opponent.
I'm a reviewer from variable 1, and I would like to ask the reporter that is the water bottle rocket have a multiple airflow?
multiple?
Multiple airflow. Yeah.
Can we state the question?
Is your water bottle rocket have multiple airflow? Like many airflow in your rocket? Okay. Okay. So do you think that if the water bottle, we assume that the water bottle rocket have multiple airflow, so do you think it's suitable to use Bernoulli's principle?
We think it's not suitable to use Bernoulli's principle, but we don't, because of the changing pressure and the mass flow rate, but we don't, the opponent doesn't really understand what is multiple airflow.
Okay. And you have mentioned that air in your water bottle rocket, this situation. So do you have any suggestion for him?
We suggest the reporter to investigate the different, like the sensitivity of the air inside the rocket for the pressure.
So do you think her suggestion is good enough for your experiment?
Well, I think it's a good idea, but at the same time, we talk about how we will do future research about water-air ratio, which can also investigate how it will affect it.
Okay. And the reporter has said that he didn't consider the turbulence. So do you think that is important?
Yes, because the turbulence will, the phenomenon of turbulence will be more obvious in the higher pressure conditions, and we think that they could have like explained the error between those.
And I think that you don't have any error bar in your chart.
Error bar. Yeah.
You don't have any error bar.
Yeah.
So do you sure that you don't have any error in your experiment? Or why you don't have any error bar?
So we show how we actually compare our theoretical diagram and our experimental diagram, and it seems like there's a little bit up and down.
Where is they have a little bit of the
Well, since we use trackers to manually artificially track the tip point of the rocket, which might cause a very little error.
So do you have any like any?
Okay, time's up. Preparation of reviewer for 2 minutes. 不用，他切完。
那没办法，要直接。
哦，这边直接嘛。
对，要拔完之后他们才会 sense 到。对，如果同时有的话，他都没办法直接切。
以前会有个 switch， 现在没有，就他们拔掉，他们就拔掉，他接就可以。Okay, comes up.
I'm a reviewer from variable 1, and it's a problem statement. And the overview that he observed that the tumble before reaching max height and the vertical to ground. And the theory he used is the thrust and the conservation of momentum and the Bernoulli's equation and the theoretic expansion and the constant steady condition. And for the experiment that he had measured the drag coefficient, boundary condition, different volume of water, different pressure, and without points, and different weights. It's random variables. Yeah. And for the discussion that he has said, as the water increase, the acceleration decrease, and as the pressure increase, acceleration. Yeah. And one improves stability, increase rocket's coefficient, not effect acceleration, and air resistance behavior will decrease quickly. And the strength for reported that he has a clear explanation, and the suggestion for him is that he lack of data and no quantitative result, and no clear level process, so we don't really understand how he did the experiment, and the data isn't accurate enough. And the strength of her opponent that she asked the detail of the experiment, but the suggestion for her is she didn't ask question about the report. And the discussion part that the opponent asked, did you measure the pressure of the experiment? And the answer from the reporter is he didn't measure that. And the question from the opponent, the flow rate remained the same, and he said yes. Oh, and we think that he should measure the air pressure like the whole time. And we think that the flow rate will decrease during the deep time. And the water volume increase and the pressure decrease. Variation rate didn't the same, and the reporter say there might be different, and we think that he should use a linear relation to change the pressure. And she asked that the width of the bottle, and he say it's the smaller will be the faster. And she asked that only a 0.1 second of the process, and he said yes. And we think that the theory concludes the whole process. The reporter should analyze the whole process. And she asked us, did you think there will be the boundary of the most of the volume? And he said there might be a boundary. And we think I use a theory to calculate the limit and experiment data to prove it. And I asked that, I saw there's no error bar in your chart, so do you sure that you have any error in your experiment? But he said, yeah, he has an error in his experiments, but he didn't use the error bar. And I also asked that the multiple airflow question. And I think that
Hands up.
there.
Concluding remark of the reporter, 2 minutes.
Well, the opponent asked about how the lift-off process definition, and we define it as the 0.1 second interval. And talking about air and water amount, we say that different amount of water with same acceleration. The change in volume of water in the bottle, we declare that it might can be discussed in the future research about water-air ratio experiments. And we talk about how will there be a side motion since we assume that it is a 1D motion. And we mentioned side motion will only after the lift-off period. So, also again, it's a 1D motion in our theory. Talk about the change of flow rate. Yeah, we do admit that it might gradually decrease. However, the flow rate is only a tool in our to get our final equation. So we won't actually need to calculate that. Talk about how the nozzle size will affect the acceleration, and of course, the smaller of the nozzle will give us a larger thrust and more acceleration. However, we also admit that maybe there will be a minimum size of the nozzle. Then the opponent talked about the change in nozzle shape and its effect to acceleration. Yeah, again, it do affect the acceleration. And he talked about how the minimum boundary and also how our experimental setup will have friction. And yes, talking about error bar, we said we have compared experimental and theoretical diagram, and also the tracker may cost one another.
Okay, thumbs up. Question of jury, 5 minutes. Any question?
I remember when I studied the rocket in the first year physics, there is a major quantity we call it thrust. Its definition of thrust is dm over dt. Can you tell me a little bit about that concept? What is thrust, and what kind of quantity is that?
Well, we think that the thrust.
dm over dt, we know. But why we introduce thrust?
Well,
why is it important? Give us a little bit explanation.
Take water bottle rocket as an example. The thrust is how the pressure will give the water downforce, which is an action, and therefore there will be a reaction to the rocket itself.
I know. I mean, the mass is decreased. The mass is decreased, of course. That's how the rocket would get the momentum. Why we use this? What kind of concept of thrust is? It's energy. It's a force. What kind of?
In our presentation, it's a force.
It's a force. Why is it a force?
Well, we state it as reaction force corresponding to the water force that is forcing downwards. It's a reaction force to the water force acting downward.
Okay, maybe the same question for you.
I think that it's a big force, and it's a main reason that the water bottle rocket will lift off.
How about you?
Because I didn't mention in our opponent what is the thrust. It's like the force that makes the water bottle rocket to lift off.
You said it's a force. So this kind of force, what's the difference between this kind of force compared to other force?
the mass of the water will mainly affect these flows.
Maybe I will explain after the story.
Any question? Okay.
And so I have a question about the theory, because in the reporter's report, you mentioned about the adiabatic extension, right? So why that is important in this experiment? And the other two, can you give some comments about this?
Should I answer? Okay. So it's not an adiabatic expansion, which means there's might be a change of heat and there might be heat loss. Then we can't use the P equals TT equals constant in our equation.
So why is that important?
Which is TT constant.
I mean, why is that important in this case? Why you have to consider the adiabatic process?
Well, since in our equation we want to talk about how the pressure will affect the force acting on the water, which basically is causing the frost force, and so when we want to consider how the pressure will change, we need to use the PV gamma equals TT in the condition of the adiabatic expansion.
The opponent thinks that the adiabatic process only appears when the air inside the water bottle rocket expands, and the speed of the expansion is very fast, and the heat will not exchange with the outer. And we think the adiabatic process is to calculate the change, like has a relationship between the changing of the pressure, and which the opponent thinks that the reporter thinks that there will be a adiabatic process, but they didn't consider the changing of the area of the water, the area of the air and its expansion.
I think the heat will lose during this process. So the PV before the process will equal to the PV after this process.
Any questions? Okay, I think time is up. Okay, please write down the score. Okay, I think we finished the score. So first we will show the score of the reporter. Okay, the score is 6, 5, 5, and 5. Okay. Next is the opponent. Okay. Next is the score of opponent. 6, 7, 6, 7, and 6. And the last score is the score of the reviewer. Okay. The score is 5, 5, 5, 6, and 6. Okay. Okay, thank you. I think we finished this round of the fight. Any comment on the jury? No? Okay. 好，那我 想我们休息。
Okay. I gave 3.6. I can't tell the, it's not too good. Okay, I think the rocket problem is rather complicated. It's really considered. I forgot I asked you the PSI. What is PSI? How? PSI is a pressure unit. How big is the PSI? I mean, no, just, I don't think we should have talked a lot of mathematics. I mean, just give us some simple idea, then tell us what's the most important parameter. Yeah. Threshed, I think that's crucial. dm over dt is very, very unusual because the force equals dp over dt, the conservation momentum. Usually we assume mass is a constant. Only this problem will consider mass is not a problem. Instead, velocity is a constant. So every parameter will affect dma dt will affect your rocket. That's my guess, my opinion. Yeah. Okay. Thank you.
Thank you. 来 ，OK， 好，那我们休息10分钟啊。请各组先换场啊，那个。
因为